He leads AI research at Krea, which is one of the leading creative AI technology and creative AI tools in the Valley here. They recently raised a whopping $80 million with over $500 million valuation. So congratulations on that. And I'm really excited to be for him to be making this announcement. So please help me welcome to the stage Sangwu Lee.
Cool. Sounds good. So I'm Sangwu. I do some AI stuff at Krea. I usually work with image models. The actual project lead was Erwan, who worked on this, but he's on vacation in Mauritius, probably enjoying a nice time at the beach. So I will be presenting on his behalf. So we released a real-time video stuff a while back. This was running with a camera feed on top of the WAN 1.4 billion model, so relatively small model. And then you can feed it into a camera feed, and then you can do video to video in real time. The prompt for this is hyper-realistic jellyfish floating in space. That's our office and our CEO Victor toying around with this. A little bit like this. So usually so I think you get the idea. So why real-time? I think real-time is quite important because right now video models can take up to minutes. If you ever, how many people here use VO3 here? So quite a few people. You click generate and it takes minutes to get a video and you realize, okay, this is not what you wanted. Typically people who actually work with this, they want a little bit better controllability and interactivity so that you don't have to wait 3 minutes for every iteration. So that's why I think a lot of people are focusing on real-time application. And this is another video. So this another cool demo, this was also on top of our 1 billion model. You can actually feed the stream to Blender to render this real time here. The rendering driving video is synced with the video, so that it's a little bit easier to compare. This one is my favorite one with my favorite one. Honestly, I don't know how he does this. Quite impressive. Quite that he can actually squeeze out a lot from our model, but so little bit of I'll be going into little bit of technical detail on how we trained the 14 billion real-time model. So usually when you train a video diffusion model, you have a fully directional model, which means that you just you have 5 seconds of frames, and you denoise that entirely, so you cannot get. Maybe you can see a preview, but you can't really render stuff frame by frame, which limits streamability or streamability. So the question is, how do we train from bidirectional model and then get it down to autoregressive model so that we can give the users frames as they generate, similar to how text autoregressive models work. They give you text by text so that you don't have to wait 3 hours to get a response. You actually get a streaming output. So how do we do this? We do it through pretty much a 3-stage distillation step. The first step is time step distillation. Typically, a fully bidirectional model takes quite a few seconds or a lot of steps to generate denoise a full video. So what people typically do is they do something called time step distillation, so that instead of doing 30 steps to generate a video, you can generate a video with 4 steps. So that's just the first step. And the second step is actually making this model autoregressive. At stage 1, you can sample a video with 4 to 8 steps, but you still need to denoise the full video in chunks. But after you do time step distillation, you do autoregressive distillation so that you can make the model real time or stream outputs. And then the third step is something called self-forcing distillation, which is actually making the model good. So the first step is relatively easy, time step plus CFG distillation. Light X2V has already done this for the 14 billion model. Wonderful. So no need to reinvent the wheels there. So we already have our time step and CFG distillation. And then the second part is auto-regressive distillation. Here, how we do it is that we take the teacher model, which is the undistilled version of which has like the highest quality, and you generate like synthetic OD like trajectories. So basically synthetic outputs from the teacher model, and then what you do is that you take the time-step distilled model, apply block causal masking, so you turn the model into auto-regressive model, and you basically try to make the student model, which is now auto-regressive, try to match the output from the big teacher model. And you might ask, why not just use real images? Turns out that the model is has way easier time learning synthetic video outputs, so that's why we use synthetic video denoising trajectories from the teacher model. And then this is step 3. This is a technique called self-forcing. So one problem people have been trying to do this auto-regressive video streaming solutions for a while. There are different methods. First is teacher forcing, second is diffusion forcing, and third is self-forcing, which is the technique that we ended up using. The problem with teacher forcing or diffusion forcing is that when you train the model, you condition the model on a real sample. But when you actually do the sampling at inference time, what ends up happening is that the images, the previous frame that you're looking at is a generation from the model itself. It's not a real frame. So the problem is that what the model is, the previous frames that the model was seeing at train time is typically an actual frame from a video. But when you actually try to run it, you're looking at a frame that you generated yourself. So there's this train test time mismatch there, and that's what self-forcing does to mitigate this issue. So kind of the core insight from the paper is that there is a train test mismatch. The model is not getting the exact frames that it was trained on. And then the second insight they have is that, well, the problem is that how do you make sure that the frames that are generated from your model is actually good? That's where they use distribution matching loss for quality. So that kind of handles two of these problems. So the problem is that most of these models are typically trained at small scale, 1 to 2 billion. The problem is that when you try to do a training with 14 billion models, a lot of problems come out, especially related to memory. So for example, the distribution matching loss that self-forcing uses, it requires a real score model, critic model, the student model you're actually training, and then an EMA model. So that's already 14 billion models running on your GPUs. And you also need to and the student model also needs to auto-regressively generate the frames, and you also have the KV cache for the past frames. So that's a lot of memory overhead. The problem, and even if you use 64 H100s, which sounds like a lot, you still get out of memory errors. So we end up using these 3 lovely tricks to handle that. One is dynamic cache management. Second is gradient checkpointing, which is typically used to reduce memory consumption. And then FSDP, DP specifically 0-3 sharding to handle some memory stuff. But I'll get into a little bit of details on this. So dynamic KB cache management, how do we do this? Gradient checkpointing typically helps reduce memory pressure, but the problem is that KB cache, when you're doing gradient checkpointing, you're recomputing the activations so that you don't have to save them. So you're doing activation computation on the fly, so that you have less memory overhead. The problem is that now you need a KB cache to actually do the recomputation. And turns out that this takes up 26 gigabytes per GPU. H100 is 80 gigs of GPU, so this is already quite a bit. So how do we handle this memory issue? We do something called a dynamic cache eviction. So if you look at how you actually train a self-forced model with self-forcing, let's say you have a transformer with 3 blocks, and you're trying to do like causal-wise block decoding with three blocks. So you do your you generate your first block of frames, and then you go to the next one, and then you use the KB cache from the previous frames to generate the next one, and then same for the frame blocks 3. Now, and that was for the forward step, but when you do the backward step, one optimization you can do is that when you do this backprop, you realize that, oh, like I don't need this when I'm trying to like backprop through like frame block 1 or like frame block 0. So as you're like as you're doing backprop, what you can do is that you can attach a small like post-backward hook to release the KB cache for each of these blocks. So like this helps alleviate a lot of memory, and you can actually train a 14B model with all of these tricks in place. And then these are like kind of like how things look. So just to get people like a sense of like how do results look like at each of the stages. When you start with like time step distillation, this is how it looks like. When you do autoregressive adaptation, you see that it's autoregressive, but the quality is not there. So this is actually, so the first step is making sure it's fast. Second step is making sure that it's actually autoregressive or streamable, but then the quality is not there. And then after that, we use self-forcing to actually improve the quality. And there are like a bunch of like inference challenges. Of course, like these are already mentioned in self-forcing paper. The weird thing about the one autoencoder is that like it takes the first frame, encodes that as the image, and all the subsequent frames, it does like 4x temporal compression, which is like kind of like weird. So the problem that you end up like having with like self-forcing or specifically with one autoencoder is that the first frame is encoded as an image, so it has a different image distribution. So what happens is that like as you like stream your outputs, as you start streaming your outputs, at some point you're going to like have a situation where the first frame that's in the KB cache is not the image latent. So that can cause some problems. So for example, like this is what happens if you run a naive strategy for a long time. So as you like run the model for a very, very long time with like self-forcing, you get like these kind of like bugs. At some point, like the model outputs gets like quite unusable. So, and another problem is that error accumulation. Your model is not perfect at generating frames, so errors accumulate. Maybe Jan LeCun was actually like right. The autoregressive generation models are doomed because we get infinite error accumulation. So how do we fix all of these issues? So one thing that with the first frame issue that we have, one thing that we can do is that, okay, like screw it, let's just like keep the first frame always in the KB cache. This kind of works, and this was actually our like first solution, kind of inspired by the streaming LLM paper. I believe the solution that the self-forcing authors used was like, when you train the model, let's just not have the first frame as a latent, so that like we don't actually get this train test mismatch issue. And the second solution is like a little bit expensive, but we found that this was actually quite helpful for quality, which is called KB cache recomputation trick. So naively, what you do is that you generate like the first block, and then you generate the second block, and then you generate the third block, and then subsequently, if your like context window is like 3, you like evict the zeros frame and then keep generating from there. But one trick that you can do to like stop error accumulation is that you generate the zeros frame, first frame, second frame, and then what you can do is that you can just recompute the KB cache on the fly without attending to zeros frame. This way, you can kind of like stop the error accumulation, and then you'll be able to generate frame 3 from the fresh KB cache that you have. This is, of course, like more expensive, and another thing you have to do is that the first frame has to be like re-encoded by the one VAE one autoencoder. So there are some, again, it's trading off compute for quality, but at least with this, we were able to like generate some videos reliably. And there's a bunch of like future works that we can do on this. Recomputation is effective but expensive. We use flex attention a lot because that's the only semi-good kernel that supports like block sparse attention. But so it would be nice if somebody writes up a kernel, or maybe we have to write it ourselves, so that like flex attention or these block sparse kernels gets good performance as like flash attention 3 or 4, or even sage attention, which is one of the fastest ones right now. And we use like DMD loss, but we could use the ADM, APT, DMD2. There's more advanced distribution matching techniques that you could use. Maybe we can do something similar to like speculative decoding, where we have like a draft model and then have like a full like teacher model, improve the outputs or check the outputs. Maybe using even even higher compression autoencoder. That's been kind of already used in like the image domain, and a lot of work on like infra side of things. One interesting problem you can have when you're serving these models is if you have a user that starts a session and then it goes on and on, and the user, I don't know, maybe takes like a toilet break, comes back, and you need to resume. The question is if the KB cache is stored in a very specific GPU, and you want to reassign the user, and when the user restarts the session, maybe you want to like reassign the user to a different GPU. The KB cache is like maybe 30 gigs. How are you gonna move 30 gigs of like KB cache or the previous frames that the user has generated efficiently across the clusters? So there are a lot of infra stuff, of course, standard like WebRTC stuff, and even like autoencoder optimization. You'd be surprised, but autoencoder is actually one of the biggest bottlenecks for real-time video. You'd expect that generating frames is actually the biggest bottleneck, but VAE also like takes a lot of time on that. But that's future works and improvements of things. And you can go to our website and read our blog a little bit more in depth. Sorry that this was a little bit rushed. I was just told I wrote this like last night, sleep deprived. Hopefully a lot of things make sense. I'd be happy to like elaborate or like explain more in like depth. This was a little bit like technical, but I was hoping that a lot of the audience here are already like kind of like caught up on some of these things. But yeah, happy to talk after this. Yep.